Okay, so in question 21, we've got a point charge system. We've got a charge of 4.07 microcoulombs is held fixed at the origin. The second charge of negative 3.4 microcoulombs released from rest at the position of 2.9 meters. So that basically accelerate the negative charge will accelerate towards the positive charge, being attracted to that positive charge. And the mass of the second charge is 2.36 grams. What is its speed when it moves to the position 1.2 meters, 0 meters? So everything's done sort of on the x-axis. So let's just draw a picture here. Maybe I can scale everything up by a factor of 2 here on my ruler. So I'll enable the first charge, the fixed charge here, and then at 2.9 meters we have, so this is our negative 3.45 microcoulomb charge, negative. We hold this charge here, positive charge of 4.07 microcoulombs, and this original distance is 2.9 meters. And then we're looking for what is the speed of the charge when it gets to, the negative charge when it gets to 1.2 meters. Okay, so negative charge is going to feel an attractive force. This one's held and fixed in place. And so it accelerates towards here, decreasing the potential energy of the two-charge system, and then increasing the kinetic energy of the negative 3.4 microcoulomb charge, since the other one's held fixed in place. And there's a couple of ways that you can sort of consider or solve this problem. So I'm going to consider system of both charges. So that means that it's isolated. Again, ignore any gravitational interactions for all these problems. So yeah, it says here, ignore gravitational forces. So that means that the delta E of the system is 0, which means that the delta U is equal to negative delta K. Now the U for a point charge, 2-point charge system is KQ1, Q2 divided by R. So I'm trying to find the final speed. So if I can set this delta Q as negative delta K, so I'll say that the delta K is equal to negative delta U, which is equal to negative U final minus U initial, which so and I can write this as 1/2 VF squared minus VI squared. And I can write this as UI plus, minus UF if you multiply that negative sign in. So here we can say that the VI squared is 0 since it's released from rest up here. And so let's say this is 1/2 VF squared is equal to UI, so this is KQ1 Q2 over R initial minus KQ1 Q2 over R final, and we can then go ahead and I believe we have all the values at this point. If you were working out your math a little earlier, I can help you out with some of these values. So this is going to be negative 0.044 joules, and potential energy is negative. Oops, sorry, got these mixed up. This one is negative 0.044 joules. This one's negative 0.10. 5. And then we can rearrange to solve for the final. Yes, so Summarizing up here, we have 1 over mvf squared. We can take out that q1, q2, 1 over r initial minus 1 over r final, and then do our algebra to get vf. So I'm taking the square root, quite a bit of algebra. So 2 times k, q1, q2, 1 over ri minus 1 over rf, all divided by the mass of the particle, 2.36 grams. Remember to convert that to 2.36 by 10 to the minus 3 kgs, which everyone's in SI units. And yeah, so you have 2 is constant, k is constant, q1, enabling, this is, doesn't really matter since both of them are in there, but enabling this is q1, the other charge is q2. The R initial, how far away, would be 2.9 meters, the R final is 1.2 meters, and so I believe, this quantity here will be negative, but it's going to be multiplied by another negative in the product, so this has to be positive value. Divided by the mass of the particle, you should end up with the final speed of 7.2 meters per second. So that's sort of one method, is to think in terms of the changes in the potential energy. Set that equal to the negative of the delta k, so the change in potential is negative, which means the change of net energy is positive. Again, the charges are being accelerated towards each other, so their potential energy of the system is decreasing, as kinetic energy of the system is increasing. The 4.07 microcoulombs been held at rest, so the only thing that's moving is the Q2. So all of that decrease in electric potential energy has been converted to kinetic energy, and it's quite a lot of algebra to sort of work with, and you should end up with this speed. On the back of this page I'll do the sort of second method, and that some of you may have tried. You can do this also in terms of potential. Of course, the answer works out to the same. So you can take your plus charge here, figure out what potential it sets up at a distance of 5.4 meters. So let's say, 2.9, so 5.4 centimeters on my ruler. So we can call this point A, which is at 2.9 meters, versus the point B. So that's from here to here, just so I'm not confused. And then point B is here, where this distance is 1.2 meters, and it's B. So we're going to think about what is the potential difference that the charge moves through. So remembering that the delta V is delta U divided by Q, which is equal to negative delta K divided by Q. So the delta V is going to be V final minus V initial, and this would be K of the plus Q, because that's what's setting up the potential, and the other charge is moving through that potential. So this plus Q is referring to the 4.07 microcoulomb divided by R final minus K plus Q divided by R initial, and that would give you the change in potential difference. Now if you want to work out those values, it's about, the potential difference is about 17,900 volts, and then we can think about our multiplying, in a sense, this change by the charge that moves through the potential difference. So my delta K is going to be equal to my negative delta V times the Q, and this will be the Q that actually moves through the potential. So this one will refer to the negative 3.45 microcoulomb. So we'd have a negative times a positive change in voltage times a minus would give us again a positive delta K, which has to be true. And hopefully you can see here that we end up with the same solution, that if you multiply the delta V here times the negative Q, and you end up with a negative Q up here times the negative Q here, it'll give you the exact same equation as you have here. So everything works out to be the same. So again, this will be 1/2 mVf squared is equal to negative of your change in potential times your negative 3.45 by 10 to the minus 6 coulombs. So again, multiply across by 2, divide across by m, take the square root, and of course you should end up with the same speed. It's a pretty challenging two-point charge system, thinking about potentials and the electric potential energies of point charges.